Alright, so for my question, I was asked to please provide a route that could be reasonably expected to convert the starting material into the final product. In each case, more than one reaction is required, and the reactions you have learned in previous chapters may be needed to solve the problem. For my question, we started with but-1-ene, and it gave us cis-pent-2-ene. At first, what was challenging was deciphering which reaction to carry this problem through and what would be the most reasonable and efficient, but I eventually found out the best way to do this. Firstly, we see that my terminal alkene has a triple bond at the end of the chain and is reacting with a strong base known as sodium amide. When the alkene, the triple bond, is treated with a base like sodium amide, NaNH2, it leads to the removal of an acetylenic proton. This happens when the alkyne proton is more acidic and it will get abstracted, which forms an alkyne anion with Na plus ion acetylide as the counter ion for the negative charge. Then, once we add methyl bromide, the carboanion acetylide will attack the methyl group of the methyl bromide in an SN2 pathway and form the internal alkyne, which is an alkene without acidic hydrogens that is on both of the ends of the alkene, having an alkyl groups. I have also added another picture to again showcase the ions and arrows that show the removal of an acetylenic proton and showcase the bromine acting as a leaving group in an SN2 pathway. This then leads us to taking our product from the last step, which was pent-2-ene, being catalyzed by H2PdCOC3, which is metallic palladium deposited on calcium carbonate that has been conditioned with lead acetate and quinoline, which is an amine. This special catalyst is known as Lindlar's catalyst. This is used for selective reduction of a triple bond to a double bond. We use a Lindlar's catalyst by having quinoline, which acts as a catalytic poison, which means that this catalytic poison will partially deactivate the catalyst, so the catalytic activity of the palladium catalyst is drastically decreased, and so only selective or mild reduction occurs and gives us cis alkenes. Now, it is important to note that in general, if PD/H2 is used, then alkynes are directly converted into alkanes. So to avoid such problem in our reaction, we use Lindlar's catalyst, which is very selective to triple bonds, and give rise to cis alkenes, which is that double bond we see. The last piece to acknowledge in this reaction is the partial hydrogenation. Partial hydrogenation is typically a chemical reaction between a molecular hydrogen, H2, and another compound or element, usually in the presence of a catalyst such as nickel, palladium, or platinum. In this case, we are using palladium. The process is commonly employed to reduce or saturate organic compounds. We use it to reduce our triple bond into a double bond, along with the Lindlar's catalyst. The hydrogenation in regard to my problem has a syn addition of hydrogen. This is specifically when the alkene formed from an initial internal alkyne has a Z or cis configuration. Lastly, I just wanted to incorporate a photo that really showcased the entire equation step by step, kind of broke it up into two steps just so you could see it a little bit better. But again, I was asked to provide a route that could reasonably be expected to convert the starting material into the final product. We again started with but-1-ene, which had that triple bond, and then we were trying to get that product on the lower end, which shows that cis-pent-2-ene. That leads to a double bond, and this is how I did it. Thank you.